Assalamualaikum warahmatullahi wabarakatuh, and also very good morning, everyone. Thank you for giving us this opportunity to present this talk on distributed optical fiber radiation dosimetry. Just very quickly to introduce our university, Multimedia University in Malaysia. The group that we are from this fiber optics research center, where we focus on design, fabrication, and characterization of specialty optical fibers for various applications. We are quite lucky to have fabrication and characterization facilities where we can fabricate our own specialty optical fiber, and we also spend some time on simulation and modeling of such specialty optical fibers. We're a small team with 3 professors and the team with a few postdocs and also postgraduate students. Our group started working into optical fiber dosimeter as part of a project with University of Malaya back in 2013. We were looking into doped and undoped optical fibers for thermoluminescence, optically stimulated luminescence, and later on we looked into radioluminescence, and we just started looking into radiation-induced attenuation. So the talk today, which is on distributed optical fiber radiation system, what I plan to do is to talk on the background and the motivation or the need to have such a measurement system. And we look into 2 major methods, which will focus on radiation-induced attenuation and also reflectometry-based measurements. We look a bit on different materials used as the dosimeter in this distributed radiation measurements, some of the challenges and way forward, and some possible solutions and way forward. Yeah. Now, very quickly as a background, it's very obvious that there are, in some applications, a clear need to have radiation measurements over a wide area, hence the title today on distributed measurement system. For example, in nuclear power stations, where there is a need to monitor conditions around the nuclear reactors. This is for safe and efficient operations of the nuclear power station. There has been some attempts, as pointed out here in this paper, exploring the potential use of optical fiber in a distributed measurement system. So what do we really mean by distributed optical fiber radiation sensing? Firstly, I think we have to acknowledge that there is a need to accurately measure radiation dosimetry over a large area, and there is also a need to be able to measure very high doses in such applications. Optical fiber, as we know, originally was meant for communications purposes, but later gained popularity for sensing abilities because of its features, such as being immune to EM interference, being lightweight and small size, very high accuracy in measuring physical quantities like pressure, temperature, and having very high spatial resolution, and also the ability to carry out real-time monitoring of long distances. So such promising attributes are now being also looked at the possibility of using optical fibers for distributed radiation sensing. Now, just a quick background on optical fibers, just to put everybody on the same page. As we all know, is made from glass, and the structure is essentially having a a cylindrical structure. Typically, a single mode fiber would be about 125 microns in diameter. It has a core and cladding both made from glass, but the core being slightly higher in its refractive index, therefore allowing total internal reflection to allow light to propagate in the optical fiber. And one of the um, I'd say behavior of this optical fiber is very low loss. If you think about it, our single mode fibers have losses down to 0.2 dB per kilometer at the 1550 nanometer range, or 1.55 microns. But there is some attenuation, which is mainly caused by Rayleigh scattering and also absorption. Now, I mentioned this because attenuation will be one of the main features of how radiation measurements are being carried out. So as I mentioned, radiation-induced attenuation. This occurs when optical fibers are exposed to ionizing radiation, some damage leading to additional loss of the uh, propagating optical signal. So this phenomenon of radiation-induced attenuation is caused by absorption, further absorption on top of the Rayleigh scattering that already occurs in the optical fiber. However, you will see that in some cases, these losses or attenuation dynamically change. They disappear after the radiation has been removed, some within minutes, some within the hour. So you might want to call this spontaneous recovery. We'll talk about recovery a bit more detail later. And in some cases, you'll see RIA increasing linearly with increasing absorbed dose. Then at some point, it will saturate and also in some cases even reduce. So all this has dependency on the materials used in the optical fiber. Now, what causes these absorptions? So one thing that I mentioned earlier was the new color centers or defects that are being caused by the ionizing radiation. But you have to also realize that even before the irradiation was done to the optical fiber, there are already existing defects in the optical fiber, such as what you see here on the slides. I won't go into details. Yeah. Now, after being irradiated, further defects are introduced into the glass. If you look at the figure here, you will see a description or a behavior of RIA as a function of wavelength when an optical fiber is being exposed to two different dose rates and accumulated over two different total doses. Mind you, this was being exposed to a non-radiation hardened commercial optical fiber. So this would probably be your single mode fiber. Yeah. So what does happen in the fiber is these defects. You can think of it as electronic and structural modification of the SiO2 matrix. So the ionizing radiation ionizes existing defects, but can also create new point defects. Now, all this leads to new color centers that would introduce new band gaps. So hence, there will be new absorption at specific wavelengths depending on the type of defects. So there have been, various studies for different types of dopants that have been doped into the silica optical fiber, and they behave differently. And I think point out here that rare earth ions have been showing increased RIA. So in coming up with a good distributed optical fiber radiation sensing system, one needs to choose the right material that has, good sensitivity, good response over the intended application, and because RIA is also dependent on total dose rate, temperature, the wavelength that is being used to measure RIA, the launched light power. So all this has to be considered when choosing the right material to be used in the optical fiber. So talking about the right material for such applications, there has been some work done earlier. Now, for example, has been shown that pure silica core fibers are more radiation resistant or radiation hardened. They are dose rate dependent. In another example, when you have fluorine doped into such optical fibers, there has shown to have enhanced resistance to dose, further radiation hardened. Some other materials like germanium, for example, if being doped into the core of the fiber, is more sensitive to ionizing radiation. And for example, here you will see germanium having a minimum RIA at 14,000 nanometers and has a maximum RIA at UV range. So different materials will behave differently, as pointed out by earlier studies, as you can see in the references made here. Now, in particular, you'll see phosphorus doped optical fibers have been shown to be suitable for radiation sensing. They are more sensitive, having linear response from milligray up to kilogray, saturates around 100 kilogray, which is quite high, is dose rate independent, has low annealing capability. Minimum RIA is around 1 microns, which is also good for light transmission in the fiber. And it's also having high sensitivity in the visible range, and therefore making it suitable for low dose monitoring. So you'll see in such optical fiber radiation system, there are certain criteria or requirements for such a fiber will be good in this application. You'll see, for example, in terms of the dose rate, what is the range, total absorbed dose, the total absorbed dose, the resolution, and also spatial resolution, and also the temperature range. Of course, these are also very much dependent on the applications. Of course, requirements in energy physics, high energy physics facility like CERN will be different from what is being needed in space satellites, for example. Yeah. So all this distributed optical fiber radiation system is based on RIA measured in dBs per meter, which increases linearly with the absorbed dose. Now, when being used with a optical time domain reflectometer, or in short OTDR, one would be able to resolve the absorbed dose at a specific location. Yeah, and now how is RIA being measured? This is a typical example as reported in a conference paper here. You can look at the reference. A cobalt-60 is the radiation source, and in this setup, there are 2 light sources being used and 3 different optical fibers being looped close to the cobalt-60 source, and 1 fiber is being the reference. So one can then compare one fiber that has not been exposed to the cobalt-60 and another 2 types of fiber that has been exposed to the cobalt-60 source. So with the data loggers, these are all automated to then measure the RIA over time, and of course this is of a known dose rate, and hence you would be able to compute what is the total amount of dose being absorbed by the fiber. Here's an example of a RIA measurement results, yeah, measured in dB per kilometer. In this case, it is a multi-mode fiber versus absorbed dose for various dose rates. And on the x-axis, you have the absorbed dose in gray. So you can see the linear behavior, and we can see some dependency on dose rates, but in general, it is linear RIA versus absorbed. Now, our team also attempted at measuring RIA, in this case for a radiation hardened fiber, a pure silica fiber. In this case, it was also a low hydroxyl pure silica optical fiber in an electron beam facility. We exposed it under a few different currents, and therefore at a few absorbed dose. And we had used a white LED to characterize the RIA through this fiber. This is the RIA measured in this case because we also measured it using a spectrometer. We were able to not only look at the RIA alone, but also a behavior of RIA spectrum, yeah, across this wavelength of interest. So the two traces reflect 10 kilo gray and 70 kilo gray with very high RIA at 460 nanometer and 550 nanometers. Now, how does the system resolve for location? As I mentioned earlier, it is based on the time of light, which is used in the optical time domain reflectometer, which is used originally for the telecommunications industry to locate events or fiber breaks so that they can go and repair the optical fiber as it faces these breaks. So what happens in an OTDR is that the OTDR has a pulsed laser that produces a series of pulses, and that series of pulses travel in the fiber, and those pulses scatter back because of really scattering along the fiber, and the information is gathered based on the time of flight. One would then be able to resolve where those pulses had been reflected from, and it is also plotted against intensity. And so on the y-axis, one can resolve the RIA. On the x-axis, one can resolve the location. Yeah, so once we can identify the optical loss at a specific location, the RIA is known, and we can use the earlier known RIA characteristics to resolve what is the absorbed dose at that particular position. So if one was to zoom into that trace, for example here, you'll see that this fiber has minimal attenuation, and only at this point you'll see a sharp decline due to exposure to ionizing radiation, and after 92-93 meters, the fiber is no longer being exposed to radiation. The attenuation flatten off again. So if one was to zoom in, you would be able to zoom in at the location. This is on the x-axis, and on the y-axis, one would be able to know what is the loss. So then the localization of how much absorbed dose at particular location can be measured. In this case, after measurement, you'll see that it has reduced to 200 gray. Now, what are the challenges faced by such a system? One of it is the reduction of RIA after the ionizing radiation. This is due to photobleaching, for example. when the RIA measurements is being done, the light propagating in the fiber bleaches the defects, therefore reducing the RIA and make the measurements in this case less accurate. There's also natural recovery from ambient light, from ambient thermal sources as well. So you can see here, for example, as reported in this paper or in this book, how over time the RIA reduces. Yeah? So this would lead to some inaccurate measurement of the absorbed dose over a distributed area. Now, in the case of photobleaching, as I mentioned, it is the case for recombination of some metastable radiation-induced color centers or absorption bands, and this is assisted by the energy coming from the light propagating in the optical fiber. So if you look at this diagram as reported here in this paper, you'll see that when the light being used to characterize RIA is 200 nanowatts, it will be this trace up here. But when you use a higher optical power for that light source at 2 milliwatts, for example, the recorded RIA is lower. So there's a difference here that would lead to an inaccurate measurement of the absorbed dose being measured earlier by this particular fiber. Now, as I mentioned, RIA is lowered because of the power or the energy being provided to the fiber to produce recombination. In some cases, ambient temperature also may affect the RIA, yeah, depending on the materials or the composition in the fiber. And this phenomenon is dependent on both, yeah, the optical and thermal properties of the RIA defects. Then when it comes to the measurements of RIA, it has been recommended that lower optical signal being used to minimize photo bleaching, and the RIA measurement would then reflect the real attenuation due to the ionizing radiation earlier. But on a positive note, photo bleaching can also be seen as a means to reset or anneal the fiber, erase any prior measurements. Yeah? That's something that we can also use. Now, in terms of the RIA recovery rate, as I mentioned earlier, some RIA may disappear within minutes, some within the hour. In the case of, in this case, it is because of the energy assisted provided by the thermal or optical sources, and this will then influence the rate at which the RIA recovery happens. Yeah. Using the earlier setup, we also attempted at measuring the RIA recovery for the same fiber, and you'll see here we made measurements using these pulsed white LED before the irradiation, during the irradiation, and after, at three specific wavelengths at 459 nanometers, 533, and 671. So you'll see how the RIA is increasing, or you see here the pulses reducing in intensity during the irradiation. But after the irradiation ceases, the RIA tends to recover, yeah, and probably in this case, most likely being assisted by the white LED at very high power of 32 milliwatts. Now, overall, you see how from the RIA spectrum point of view over time, how the RIA was here earlier in the right after the irradiation stopped, and then how the RIA started to reduce over time. Now, what are the possible solutions to overcome such challenges? I'd say the improvement of the accuracy by measuring RIA after the photo bleaching can be as a means to erase memory of past measurements. Let's use it on a positive tone. Now, this can then clean from possible unwanted recovery. So every time a measurement of RIA is being made, you erase any prior measurement. So you start clean. Now, in order to do this, one would require materials or code opens in the fiber that has improved sensitivity, perhaps down to 0.1 dB per meter, at exposures down to milligray, and of course, all this depends on the applications. Has to be stable and not recover due to ambient or rather annealing at room temperature, for example, at 25 degrees C. Has to be stable also not to recover due to the propagating light, which is larger than 1 microwatts. So these are things that has to be studied further. Understanding of RIA and the recovery kinetics in this case will be very important. Now, in order to realize some of these possible solutions, I strongly believe that this is where studies in specialty optical fiber, where one can design new optical fibers and looking at different dimensions, structures, dopants, and coatings can be put to good use. Some of the new methods that I think is worthy of mentioning here is to have high resolution measurements in distributed optical fiber radiation sensing systems based on RIA, especially looking at how ionizing radiation changes the refractive index. Now, once we can realize a suitable optical fiber, a specialty optical fiber having this ability, we can use phase sensitive OTDR, or what is also known as coherent phase OTDR. And we can, with this ability, we can explore new applications for brachytherapy dosimetry, for example, in the oil and gas industry, gamma ray logging. If one was to carry out forensics in a nuclear accident, fiber optics can be a good use. In this case, to have distributed measurement, and also for 2D and 3D dosimetry. Now, very quickly about coherent phase OTDR, it's similar to what I mentioned earlier, the use of OTDR, but you might want to think of it as a combination of OTDR and interferometry, combining the two, yeah, being able to locate the intrusion, in this case the change of refractive index caused by the ionizing radiation. And with this COTDR, one can have higher resolution and also having the ability to measure and localize the ionizing radiation in real time. One example of such application I was mentioning earlier is brachytherapy dosimetry. You can see the photo how an optical fiber sensor is being used by a group of researchers from University of Limerick for low dose rate brachytherapy. So the size is just perfect, but in this case, if we were to couple the material suitable for COTDR, having the right sensitivity, one would be able to deliver dose distribution measurements in clinical high dose brachytherapy. So in conclusion, I believe the radiation measurements over large areas are very crucial. There are many applications that require this, and distributed optical fiber sensing system has demonstrated many achievements in realizing this. And although there are several changes, as I highlighted here, in terms of the spatial resolution and the ability to measure real-time recovery and photo bleaching, this can be overcome by the right material being used in the optical fiber, coupled with a technique called coherent optical time domain reflectometry. And because this is a very cross-disciplinary kind of research, I think it requires very good collaboration across the different disciplines. I'd like to end this by saying let's collaborate and work together. So thank you very much for your attention. Should you need to contact me, this is my email address. Thank you and have a very nice conference. Bye.